And I think we're all set. So please, Kostas, take it away. I'm going to turn off my video just for bandwidth. Thanks.
Okay, thanks a lot, Clara, and thanks everybody for being here. I'm going to present you some work that I have been involved with in the last, say, 5 years, all of them related with volcanoes, one way or another. And I left this beyond part as some discussion that I will be presenting at the very end of the presentation about things that are related with volcanoes, that I am involved with some projects that are newly funded for planets or planetary bodies, better, outside Earth. So let's start from volcanoes and some fancy photos. This is a picture taken less than 2 months ago from an ongoing eruption going on in Iceland. And you might have seen some things in the news in the past. The news have lost interest since this eruption started, because nothing really much is happening. If you see this exact same day from a different perspective, it's not so as magnificent as you might think from the first one. So volcanoes can be something that can really devastate their surroundings, and even the climate of the planet can be affected. But it can be something like muted, like this eruption here. I'm not going to be discussing about eruptions that are happening into the troposphere and they stay there, but instead I'm going to be discussing about eruptions that are large enough to penetrate the stratosphere and affect the climate of the planet in larger or smaller magnitudes. So I'll start with some people that have contributed to this work, and I want to highlight that all of them have been very important in their own roles. And I am having like Susanna Bauer, Allegra Grant, Marcus, who is doing some Latin hypercube work that I'm going to be presenting. Sergey is doing some development that we are now taking into our model. Ram, and who is a postdoc right now that I'm going to also show some work related with his stuff. Gera Stenchikov is working with Sergey, and Helen is helping us with the volume simulations. And then we have a new postdoc, Zachary McGraw, who is, which I am co-advising with Lorenzo Polvani. I'm not going to show any results from his work yet. That's why the gap there in the extra space. But I will be doing that in probably my next presentation about volcanoes. And then for the planetary studies, we have some work related with the ancient moon with Igor and Christopher Hamilton, who is actually sampling that very eruption I just showed you in Iceland right now. And also Sunny and Guillaume are part of that, and of course Michael Way and Eric. And with Mike Way, I have more than one project related with volcanoes that are, some others are also involved with it. Anyway, let's start by saying that, of course, I'm going to be discussing about models. And the main question is, how do we simulate aerosols in a model? And the way that we simulate them is, it is harder than simulating greenhouse gases, because they can be in they can participate in different ways in the model that are beyond just the greenhouse gases. So gases can condense and create particles, or they can condense on pre-existing particles and make them grow. And then particles can also evaporate depending on the system, on the environmental conditions, on the chemistry that has happened or is happening right now, and in several other ways. They are very variable in size. They can be from nanometers, which is the very, very small particles that have just been created, up to millimeters. Because if you take the strict definition of an aerosol, clouds are also aerosols. So the cloud droplets are suspended into the atmosphere, and they should be considered as aerosols in the broader sense. I'm not going to be discussing about clouds though here. They are very diverse in composition and phase. They can be solid, they can be liquid, they can be mixtures. The composition can be uniform. They can have different components in different pieces of the aerosol. So they can be very hard to model. And then their lifetime is, in general, about a week, because most of the aerosols are in the troposphere and they are susceptible to wet removal, which takes them away very effectively. But that depends on their size, their composition, and also the location. So if they are really high up in the stratosphere, they can survive for months or even years. The typical aerosols, in the sense that I will be discussing them, the smaller ones, not the cloud droplets, is mostly the size of air pollution, but other types are haze, fog, clouds, dust events, etc. There are several ways people are trying to simulate aerosols in models. The standard way is what we call a bulk approach, so they only care about the mass. The model makes an assumption about their size and their shape and any other physical parameter except the mass that is being tracked in the model. And you need to have as many tracers in your model to track as many components you have in your aerosols. And this is what we use for OMA. And then there is a sectional approach that essentially is the same with bulk, but only there are several sizes. And then there is a way to transfer mass from one size to the other. And since there are smaller sections of discrete sizes, then we can calculate also the number concentration in those, and then we can construct some size distribution. That is, it can have some random shape, as an example you can see here. This is an expensive way to do it, and we used to have this Thomas model in the GISS model to simulate it, but we do not have the manpower to keep it up to date anymore, so we are not using it anymore. And instead, we're using matrix, which is what I will be showing you results today, which is a model. So it assumes that there are different size classes and different composition classes in the aerosol population, but these are not very narrowly defined in size. They have a normal distribution, they have a width, and then the combination of those gives us the net size distribution. There are very few models that are particle resolved. They really track every individual particle and you analyze them statistically, but this is nothing that we can actually include in a global model because it is just way too expensive. So I'm not going to be discussing about that anymore, but you just need to be aware that these models do exist. So there is a simpler way before going into the tracers and simulating them in a model. There is an even simpler way to do it. And and as an example of the volcanoes here, you see on the x-axis the time, and this is roughly a little bit over the last millennium, and the radiative forcing of the different forcing agents. And I want you to focus on those blue and orange lines, which are two different realizations of a volcanic forcing. So instead of the model having to simulate the sources, the sinks, and the transport of aerosols into the whole atmosphere, then the cheap way is to prescribe some external forcing and then see how the climate behaves on that. And these are some ways that people have done it in the past, and we are still, and we are still moving into the and we're still doing that into the model. But this is encapsulating too many things that are changing at the same time, and it is not as accurate as simulating the prognostic tracers, even if you have uncertainties in the simulation of the prognostic tracers. So to simulate volcanism, I'm going to show you how we do it with matrix and in the model, and we have done a lot of different things. And but the main idea is this: you inject some mass into the atmosphere, and this mass can be SO2, it can be ash, we do not have that, it can be water, it can be other things. SO2 is the key thing that is involving aerosols that is important for everything I'm going to be discussing here. This SO2 is having some chemistry that converts it into sulfate aerosol. And this chemistry is heavily involving the OH radical, which is a function of the photons available at those locations. Then sulfate aerosol can be removed. Obviously, SO2 can also be removed. But sulfate aerosol can be removed. It can sediment, or through the Brewer adsorption, it goes to the poles and then falls down there. But while it is airborne, it can either scatter the solar radiation back to space, or it can absorb the infrared coming from below and heat this aerosol layer right there. And there are other things that can happen, like it affects diffuse radiation and stuff. But the key points is the shortwave and the long wave effects that are happening, and also the fact that they can serve as heterogeneous chemistry medium, and they can affect stratospheric ozone, for example. But I'm going to discuss about that very, very little. Now, in the CMIP world, we have VolMIP, which is a modeling and comparison project that studies the volcanic effect of aerosols, the effect of volcanic aerosols in the different models that participate in CMIP6. And the VolMIP is interested in this red box. They don't care about how you are creating the aerosols and how you put them in the stratosphere, but they do care about how the presence of those aerosols is affecting the climate. And there are several sensitivities. There are experiments that study Pinatubo, they study Tambora, they study multiple eruptions one after the other. There are several cases. So I'm going to present you the simulations that we've done with a Pinatubo experiment happening in some pre-industrial state. And this is with a very, very simple approach that I told you at the beginning. We prescribe an aerosol layer into the stratosphere, and then we see what happens to the climate. So forget about the colors inside this plot for just a minute. I'll come to the colors right in a minute, but just for now, just think of those as a cloud of dots. And in the x-axis, it is the ENSO index. So the negative is La Nina and the positive is El Nino. And then on the y-axis, we have the negative and positive NAO, the North Atlantic Oscillation. And then we have sampled 400 years of a pre-industrial control from the GISS simulation. And we see all those dots here. Again, forget about the colors. And there is a cloud that you can see spans across both positive and negative NAOs, positive and negative ENSOs. And then from those, we picked cases where three cases for NAO, very negative, very positive, or neutral. Three cases of ENSO, very negative, very positive, or neutral. And then we did, for those 9 cases, we did 9 ensembles each. So we picked essentially 9 cases of each one of those. And these are the colors. So the red dots that are like blobs here, here, and here, and then 1, 2, 3 again, and 1, 2, 3 again, are the 3 times 3 cases of the positive, negative, and neutral ENSO and NA. And then on top of that, we say, you know what? This is clearly sample biased, but by design, obviously, so we are aware of that. And then we say, let's see, however, how a totally random sampling will happen, will give us, what it will give us. And then these are the blue crosses here. And you see that they are more uniformly distributed around, and some of those blue crosses coincide with, happen to be the same with those red ones. So in any case, we have a large number of simulations that we have sampled. And then we said, okay, given what happens with those indices in a winter, and this is a time on the right axis, and this is a January and December. So, and then January again, December, January, December, etc., 4 years. Depending on what happens on this winter, let's get an eruption in the summer before and see how those indices are being affected right here and how this evolves as well. And as I said, Pinatubo-like eruption, just assuming that the optical depth of aerosols is as measured for the 1991 case, but only in the pre-industrial atmosphere. And we simulate 3 years. So this is the time evolution of the global surface temperature, global mean surface temperature at the top, and just the tropical part at the bottom. And you see that at the beginning, and these are anomalies. So at the beginning, nothing really changes because no eruption has happened yet. So all the lines are right together with the control. And then the eruption is right here, and then there is a response. And you see that the mean is the black line, and then with the 3 different colors, we have the different ENSOs, and I'm not going to show you the NAO here of interest of time. And it doesn't differ so much. In the tropics, there is a bigger difference, so you see that the negative ENSO deviates more from the other two, so it appears that it is showing something different. So that's the first interesting thing to see. Then, if you want to see if you split that into positive, negative, and neutral ENSOs, and you want to see the actual statistical analysis, you see that the eruption is here, and this is the difference between the control, which is the gray line, and the perturbed cases, which is the blue line. So you see that for the positive ENSO, there is a negative response here. The neutral ENSO, it is nothing really happens. The control and the anomaly is falling right there. And then with the negative ENSO, we see that the anomaly is about 0. And the positive ENSO has a negative anomaly. The neutral ENSO has a negative anomaly, and the negative ENSO has nearly 0 anomaly. And we have that we're ready to submit this paper very soon. And so I'm not going to discuss about the mechanisms that this drives it. We submitted this paper in the past, and the reviewers asked to say a little bit more about the mechanisms, so we're working on that. The interesting thing here that I want you to keep is that it appears that if the negative when you have an El Nino, it appears that this El Nino weakens. If you have neutral conditions, it appears that the model is trying to go towards a La Nina case, but it doesn't really go there because it is very weak. So it looks like there's a negative anomaly here, but it's not very strong. And then for the negative ENSO, it appears that nothing much happens, maybe because the model is already too negative in terms of index, so it is hard to push further down.
Kostas?
Yes.
Yeah, so we have one question in the chat from James Acker. The question is, wasn't the 1982 to 1983 ENSO signal delayed by the El Chichon aerosol?
I don't remember off the top of my head, but we did not study the El Chichon here. So El Chichon was a different case. It is roughly at the same latitude with Pinatubo. It is a smaller magnitude though, and it is a different season. So I would expect to have a little bit of different response, but I will have to check for El Chichon to say more about that. Sorry.
Great, thanks.
So, and then just one plot for NAO. This is the lower stratospheric temperature from the South Pole down here to the North Pole on the right. And you see that the mean state is this blue line, the black line, and the negative and NAO falls right there. So there is nothing happening really with the neutral NAO. But then when we have negative NAO, the stratosphere appears to be cooling compared in the North Pole area compared to the neutral or the mean state, but it gets warmed up in the positive NAO. And the important thing to keep in mind here is that we are on purpose doing the sample bias. So the if you sample randomly a control simulation that has all the different states of NAO and so, and you try to see what happens, you will probably fall into the green envelope here. And then you will not be able to see any response. That does not mean that there is no response at all. Based on those results, what we see is that if you do several eruptions and you try to see what happens on average, you will probably don't see anything. But if you do see an eruption that happens at those extreme NAO cases, the very positive or very negative, then chances are that you will be seeing a signal, which is, so we will, if you want to see, for example, if Pinatubo created this, you need to see whether during the Pinatubo case, we were in the negative or positive NAO. And that applies to any volcano, obviously. So,
Kostas?
Yeah.
So, just because there's one question on that. So, Gavin, do you want to unmute? Okay. Gavin does not want to unmute. So Gavin asks, surely what you are seeing is that the selection on future NAO is not relevant?
Of future NAO? I don't know what future means, but I would say that...
All right, let me unmute then.
Okay.
So you're selecting on the NAO that's going to in the winter following when the eruption is happening. So you're selecting on the future state of NAO, right? And then you start the eruption 6 months.
Okay. Yes. Yes.
Right?
Yes.
So, but what you have is that regardless of whether you pick the high-end NAOs in 6 months' time, or the low-end NAOs in 6 months' time, or the neutral NAOs in 6 months' time, your distribution of what actually happened 6 months after the eruption is identical. So that just means that it's not relevant what you did.
It means that if there was a state to happen, it might have been affected. But
no, because the distribution, regardless of your selection, is the same.
You mean in the negative case?
In all of the cases, they're right on top of each other.
Well, this one is not on top of the blue one, right? The red is not on top of the blue.
No, but that's the delta.
The green is also the delta for the neutral NAO.
Well, the neutral NAO is 0. So if I'm actually plotting the actual NAO, not the delta, right?
Yeah.
Then I'm going to see that all of them are on the same thing. You spelled stratospheric wrong, by the way. That's okay.
I think that we need to see this equivalent figure for NAO, which I do not have here handy.
Right. I think it was in the original document, which is why I was confident in what I was saying.
Yeah. So, yeah, it's the NAO index is a different story from the lower stratospheric temperature that we're seeing here, right? So right. I'm not saying here that if in 6 months' time the NAO was supposed to be negative, and then we say, okay, let's let the volcano go off 6 months early and see what happens to the NAO. I'm not saying that. I'm only saying that in a potential negative NAO in a winter, if there is an eruption going on 6 months earlier, the stratosphere will be cooler. That's what I'm saying. Does that make sense?
Oh yeah. No, that's fine. That's fine.
Okay.
Sorry.
Okay. So all those simulations that I showed you are with imposing a stratospheric aerosol optical depth, which is essentially like imposing an external forcing and trying to simulate what happens. This is not that simple though. So VolMap has the goal to study the climate, but if you want to really understand how exactly the processes of the volcanic eruption are happening, you need much more than that. So a little bit of chemistry. In the stratosphere, we have the Chapman cycle. You have ozone being photolyzed, and then the products of the photolysis get recombined and give you back ozone, and you have a null cycle. You also have higher energy photons that can produce this O1D radical, which is the atomic oxygen in an excited state that is more reactive. But this can also hit any random oxygen or nitrogen around it, and it will lose the extra energy and go down to the basic state, and then it will combine to form ozone, so there is a null cycle. However, if there is water around, this O1D will form OH radicals. And this is a major pathway for having OH radicals in the atmosphere. And these OH radicals will attack SO2 if they have following an eruption. And following a series of reactions, they will finally form sulfate aerosols. As far as I know, nearly no model, if I would say no model at all, has all these three reactions at the bottom. They're simulations. And the presence of water here does not mean that the water is a limiting factor, because this reaction is so fast. It happens nearly instantaneously. So even in an extremely dry stratosphere, there is plenty of water for this reaction to happen nearly instantaneously. So the role of water is in this reaction, because this one is not so fast, because O1D, in order to find water, has to compete with all the oxygen and nitrogen around that will lead it into the base state. So this water, if you add the water here, it really affects the whole process. So models usually say OH plus SO2 gives you sulfate. And you also get this radical because it is necessary for keeping the radical balance right and for ozone chemistry. But water in the key point stays around. And let's see what happens very quickly. This is 6 months after the eruption, and this is South Pole and North Pole. And you need to be looking at over the color bar on what I am plotting. So SO2, this is after this SO2 is being injected here and from a Pinatubo case, and then it gets transported, and then it gets it spreads across the two hemispheres, and then gets consumed until it goes away. H2SO4, which is the gaseous precursor of aerosols, is also forming very quickly and then goes away because it has an extremely low vapor pressure, so it forms aerosols. And these aerosols that are forming here, this is a cryptic name for saying very, very small particles. They are forming and then they are disappearing as well, because as they form, they coagulate and grow, and they pick up more H2SO4, and as they grow, they form the larger particles, are the ones that survive for months and even years, if I would be to extend this plot. And these are really the ones that make a difference. That's why I saturated the plot to just make this point. And the forcing that is happening because of the shortwave forcing that we see in those 6 months is a cooling, is a negative forcing, which it means cooling for the shortwave, and the positive forcing for the long wave, which means warming. And the cooling is bigger, it goes to -35 here, this one goes to +11. So it is, the cooling dominates, but the warming is also important. So this is what happens in general. You inject something, it gets processed as it goes down, and then it has some climate impacts. Then we did some simulations with just SO2, which we call dry, SO2 plus water that we call wet. Just for fun, we did the water-only injection as a test to see that whether the water itself is making something fun. It doesn't, so you will not see anything interesting here. And we also have a control simulation. So, and we did that for both pre-industrial and present day. I'm not going to focus on the differences between the two, but they are small. The important thing is that as the time goes by, and these are global mean values, and the SO2 gets injected nearly instantaneously, and then it goes away with the wet eruption much faster than with the dry eruption. while the H2SO4 is forming much faster in the wet eruption compared to the dry eruption, because obviously whatever is being destroyed here is forming H2SO4. But this one goes away fast as well. So the chemistry is really changing. And if you see this after the second month, we're talking about factors of like 4 at least difference in the amount of SO2 that survived after 2 months. So this is a really big difference by just adding this water and the chemistry that is related with that. And in terms of particles, you see that the number concentration of the very, very small particles is not picking up higher than in between the dry and the wet eruption, but it does go away faster in the wet eruption because the particles are forming faster in a very localized area, so they get scavenged by coagulation much faster. And then there is nothing interesting to see in the size of those particles because they just go away, and this is mostly some noise from the model. And but the important thing is that the mass of those particles is forming much faster than in the wet than in the dry eruption. And if you see the same exact plots for the bigger particles, the accumulation mode, which is the one that makes actually a difference, the number concentration is not changing too much, but the size is changing quite a lot. And I'm not going to discuss about this. This is an interesting dip. I'm happy to discuss that later if you're interested in. But the important thing is that the size of those particles is, sorry, this is the number concentration, yeah. The size of the particles goes up, and the mass of those particles is forming much faster in the wet eruption compared to the dry, and then stays for months and months because you're in the stratosphere. There is no wet removal for those particles. So they really need to grow up and then settle by their sedimentation or by downwinds that happens at the poles after they get transported there. And we published this plot a few years back that shows the optical depth of the total aerosols. And there is this interesting spike for the wet eruption, which is the combination of this mass, which is very optically thick particles, very actively optically, and this one here. So you have a spike, and then it starts to go away, and then it comes back by this one. So it's a very interesting thing that I am trying to wrap up to publish for like a couple of years or more now. It will happen. Then the presence of the aerosols and SO2 has a lot of implications, and this is something that we are now putting into the model based on this study here by Sergei Osipov. And if you have, this is the vertical, on the y-axis you see the vertical, this is the surface, and this is the model top, and this is the part of the stratosphere that we care about. So if you have an eruption, you have a large amount of SO2 being injected, the red line, and this forms some aerosols, which is the blue line, and the black line is the ozone, the stratospheric ozone layer. And what you can see here is, depending on the size of the eruption, and these are 4 different sizes. The blue line is a Pinatubo case. This is a 10 times Pinatubo, 100 times, and 1,000 times. You see that the SO2 absorption of this thing here is absorbing light, and then it does not make it available for the chemistry inside the plume here. And then the larger the eruption, the more you go down in the relative change of the photolysis rates. So if you have in 1,000 times Pinatubo, you essentially shut down for the chemistry completely because everything has been absorbed. And at least for the wavelengths that this photolysis rate is, the photolysis rate of ozone matters. So for a Pinatubo case, it is not very important. It is just a few percent. But then if you go to the green line, which is a Toba eruption that happened in 75,000 years ago, million years ago, you see that this effect is pretty significant. And if you do the same exercise with the aerosol extinction, you see that the aerosols are not being affected, are not affecting the photolysis too much for a Pinatubo case. They do, but not too much. and then again the same result. And this peak here is interesting because it is essentially when you are just above or at the very beginning of the aerosol layer from top, you have the backscattering of light on the top of the aerosol layer that creates some enhanced extinction there. So some very interesting things here that we are now adding into the model, and it's going to be that Sergey has developed. Then for the Toba eruption, which is the 100 times Pinatubo, this is a complicated plot. I'm going to focus only on one thing. These are different lines. So you have then 1,000 times, 100 times concentration, and then it goes down. This is the years, and until it goes away. The interesting thing is this orange line. And the orange line shows the effect of the SO2 decay as the time goes by, if you are not taking into account the aerosol microphysics compared to the base case, which is the blue line. So if you do not take aerosol microphysics into account, you enhance the SO2 lifetime. And if you do that, your optical depth is greatly increasing compared to any other case that we studied individually. So from all the chemistry and the impact dynamics that the SO2 is doing by absorbing radiation or by the aerosols through short wave and long wave forcing, or by the chemistry that is happening with SO2, from all those effects, the inclusion of aerosol microphysics for this very large eruption is of key importance. If you do not include it, then you are up there. And the value of something like 4 to 6 is a value that a satellite like Calypso, for example, will not be able to see anything. So for 2 years, we are above the ceiling of what a satellite can see in optical depth, which is a really big thing. Just to give you a perspective of how big this value is here, that exceeds 10. So aerosol microphysics are really, really important, and that's why we use them. And one extra thing that we did with Toba is that we simulated different, the ozone column in the tropics, in Dobson units. You can see them here for no eruption, which is a standard case for Pinatubo, and then for 10, 20, 30, and 100 times. This is Toba. You see that clearly the ozone goes down just because you're affecting photochemistry so much. And this plot on the left is again the time on the x-axis and the latitude on the y, and you see nicely the seasonality of the ozone in a standard case. And you see this very big blob here, which is nearly 50% reduction of ozone for the first months of the simulation. So essentially, an eruption of that size created an ozone hole in the tropics. So this is something that our model is able to simulate, will be able to simulate extremely soon.
Sorry, Kostas, I have a question. Yeah. I think you mentioned this, but I missed it. This figure, so this is the chemistry response. How much of this could just be kind of the dynamics responding and then changing the ozone, or is this all kind of wrapped up in that?
So I don't know how much it will be, but probably we'll have those numbers for you if you want, because we have done the several different eruption sizes to study the chemistry and the photolysis effects, and then for the ozone response we focused on the actual Toba, and so we need to see whether the sensitivity studies we did are affecting ozone like this. And I mean, they will. The question is which one is making most of the contribution. And I don't have the answer, but we have the simulation, so we can take a look on that.
Okay, thanks.
I would expect that this is mostly chemistry. It must be mostly chemistry, because when you have a 50% reduction, from values that are like 250, you go down to 125. There is no place in the world that has very low values of ozone other than the troposphere, which should be irrelevant. So I don't see how dynamics alone will reduce ozone by that much, unless you are having tropospheric air coming into the stratosphere much faster, which I think is probably not the case. But we have the simulations, we can take a look.
Yep, thanks.
So going to the historical times now, and this is a project that we have with a number of partners. It is led by the Yale University, and you can also go check our website. It's pretty cool there. And so what is this project about? The idea is that this is the year from 305 before Common Era to 35. And you see with the bars here, volcanic sulfate as measured from ice cores. And then you see the triangles, which are revolts that happened in ancient Egypt or in or in Mesopotamia or in this area around the Mediterranean where we have data. And when the triangle points upwards, it is some internal revolt that happened, and when it points downwards, it correlates pretty well with volcanoes. Now you say, yeah, of course, it's just a correlation. It's not. There is no way for these things to matter. It's like the seats in the Senate correlating with sunspots, right? So, well, it's not that easy. The point is that harvesting for food was very important in ancient world, and especially for Egypt, that it is a country surrounded by desert and it is being fed by the Nile. This is a very important piece, and the Nile is being affected by climate. So if you have an eruption that is large enough to affect climate and then to affect Nile, then it might affect people and they might starve and they might revolt. That's the main idea. And this is actually being seen in the simulations. And in Simulate 5, you see at the top, if you sample the 5 largest eruptions of the 20th century and you plot the anomaly of precipitation compared to a control, compared to the mean of the 20th century, you see that there are some positive and negative anomalies. And the important thing is, this is the Nile, the blue line here, and the green area is the Nile Valley. And you see that this red part here in all the headwaters of the Nile is negative. So you have suppressed precipitation when there are eruptions happening, at least based on the 20th century simulations. And this makes the flood height that you see here of the Nile go negative, statistically significant, and this will affect, if the flooding goes below the standard, below the normal values, then flooding doesn't happen, crops fail, people starve. And this is something that is this is how we started this project. And these data are coming from the Islamic Nilometers, and these are very long time series of, there are very long time series of these, and we really see flood failures in the historical times. And this Nilometer, just for fun, is an actual building. It is not something that you go down and you measure the depth of the Nile. It's nothing like that. It's water comes in, water comes out, and then there is some person that goes down the stairs and sees where the Nile is here. So again, the same plot that I showed you earlier in a different way. So from minus 500, so 500 BCE to essentially present day. And you see that there are eruptions here. I'm not going to discuss about the temperature response for now. And then you see that there are some really large eruptions that are happening. And these eruptions are categorized as tropical when there is a red line, the northern hemisphere eruptions with a blue line, and the southern hemisphere eruptions with a brown line, which you can see some here and some others right there. So the important problem that we have when we're trying to simulate this in a model is exactly the legend. Tropical eruption doesn't really help us in any way on how to constrain this eruption and simulate it. So what they do is that they categorize a tropical eruption as an eruption that you see signal that is both present in Greenland and Antarctica at roughly the same time. Otherwise, if it is only in one of the two ice caps, then it is considered the northern or the southern one. So we say, okay, we want to do this, but how can we do it? And this is zooming in from the 200 BC to 100 BC, exactly the same plots numbers as I showed you before. And this is the pre-industrial to present day. And you see that this is Pinatubo. So there is a signal in both eruptions, in both hemispheres. And then green is Greenland and blue is Antarctica. And this is the 160s BCE, which is a very interesting period. We have a tropical eruption that happens pretty big. If you see the y-axis is different, so this is bigger than Pinatubo. And then within every 3 or 4 years, we have another and another and another, and all of them are in Greenland only. So northern hemisphere eruptions that can potentially affect that area of the Nile. So we say, okay, we want to simulate this, but how can we do it? We know nothing other than this one data point. So for this, we need to find a way to narrow down the uncertainty that we have. We know nothing about it other than some sulfate deposition. And then, so we said, okay, let's make a probability density map of eruptions, because in the past, some volcanoes have been identified by combining a wealth of data. So we are not claiming that, we can do a better job. No, we cannot do a better job without geologists and without an army of researchers. So we just want to narrow down where the volcano is and how high it went, how much SO2 was injected and everything. So we say, let's take the parameter space first. Let's define our problem. We do not know where a volcano is. So longitude and latitude is unknown. We do not know when it happened during the course of a year. We do not know from where up to where the volcanic plume got injected, whether it was even in the troposphere only or just in the stratosphere. So have a sulfate in the ice cores, it might be a volcano which is just a few kilometers away and it is just a minor event. But it might be something really, really big. And this is why we want to study this whole parameter space. And then we have no idea about the SO2 amount and the water amount. So we say, okay, let's take this. And by brute force, we need something like 4 million years of simulations and 113 years of wall time. I'm not going to go through the math of how you do that. You can read these bullet points. And 51 petabytes of unprocessed data. So the Discover supercomputer is probably too small for us, for just this one project. So the other way is a Latin hypercube approach. We have an expert at GISS to do that, to help us do it. And then we sample the parameter space in a Latin hypercube manner. And then we narrow down the amount of experiments we need to do, the amount of time that it takes for those to be done. We are down to like a week or maybe even 2 weeks of wall time and a very manageable amount of data. So the idea is that we have all those eruptions happening, and then we see how much sulfate is being deposited, and then we can say which types of eruptions are not likely to affect the results, and which eruptions are very likely some eruptions are not likely to be the ones that we're searching for, and which ones are. And we do expect that this will probably end up in a large set of the parameter space, but it will certainly be narrower than what we currently have, which is just three latitude bands. This is an example of how the sampling looks like. This is the time as a function of altitude, and the length of every bar shows you how thick the plume is at injection time, and the deeper the color, the more SO2 you have at the top and the more water you have at the bottom. And we have similar plots for longitude and latitude. So we really sample nearly everything, and then we analyze it with Latin. We will be analyzing it with a Latin hyperactive approach. Time is running up, so I'm going to finish really quickly with just a few slides about planetary scale transforming volcanism. Because volcanoes in our lifetime and the lifetime of our ancestors was pretty mild. There are major events that can affect a planet in much greater ways. And one example is the Neoproterozoic extinction and glaciation that happened, say, 700 million years ago. So this plot shows you the radiative forcing as a function of global temperature. And if you think that a planet in equilibrium has a radiative force, a net radiative forcing of roughly 0, you're about there. And if you allow an eruption to happen, then you create a negative forcing because the short wave is stronger than the long wave, as I showed you. And then that tends to cool the planet until you go back to equilibrium. However, there is a sweet spot, as it is claimed in this paper down here, that the shape is not exactly a straight line, so you miss the spot here and you go down to a snowball. So after an eruption or a series of eruptions, I don't think that we really actually know, the planet turned into a snowball, and that is extremely stable, and it takes a lot of effort to go back into an ice-free state. And this is one example of a planet that actually cools a lot because of volcanism. The other example is the exact opposite, and this is what happened, we believe, in Venus. So this is a complicated plot. I'm going only to show you this black line, essentially. But the planet starts from a magma ocean, and then it cools, and it further cools and goes into some temperate period that is pretty nice and warm. And then suddenly, major volcanism starts to happen, called which is probably equivalent with the large igneous provinces that has happened on Earth as well. So volcanoes go off a lot, and on top of SO2 that they inject, they also inject CO2, and the CO2 builds up and builds up and builds up, and then it hits the planet and creates the hellish planet that Venus is right now. The interesting thing is what happens at the beginning of this. If Venus was habitable, and it doesn't matter whether it was inhabited or not, just habitable, the presence of SO2 might have given a little bit more time to the planet itself. So consider this timeline here. This is in thousands of years, and you have some CO2 amount, and then you have some injection of volcanoes, and then you increase the CO2 level, and then some other event, you increase the CO2 level, and you keep going stepwise like this up to the present day Venus. In addition to the CO2, though, you also have the SO2 that is being injected, which forms aerosols. And these aerosols, if you go into the temperature, they might cool a bit before you get the large heating of the CO2, which is in the blue line. And the same thing happens all the time for SO2. So if these events are close enough, you might keep the planet in habitable conditions because the SO2, the sulfate layer that is being formed is masking the CO2 amount that is being added. So it is until the volcanism stops and then CO2 it suddenly heats up the atmosphere and then kills the planet. This is something that we want to study. It's a recently NASA-funded project, and it has a number of different implications. It's about comparative planetology and even detectability of exoplanets. And another project that has started like a year ago is about the early moon. This is so the previous project is led by Mike Way. This is led by Igor Alenov, and the same thing we believe happened to the moon, but again in a different way. Volcanism, and this is now in billions of years from present day, which is the zero. We believe it created a transient atmosphere on the moon. So it was volcanoes were injecting a lot of material in the atmosphere, and some thin atmosphere has been built. Whether this was an atmosphere thick enough to become something like even Mars, or it is something extremely thin, like in the microbar scale, is still under debate. The important thing is that this transient atmosphere might have served as the means of transporting water from the volcanic regions, because water is injected at the same time in the volcanic events. So the water can be transferred through the atmosphere to the polar regions and then deposit into the permanently shadowed regions, and it is still available today for even users by humans if they go there. And this is something that we're interested in studying. And some very recent results from Igor show that if you inject water from some volcanoes, and depending on the different pressure that the atmosphere is having, and you can see that here, you see the time that it takes for the water to essentially deposit from the atmosphere. But the interesting plot is here, the one on the right, which shows the surface pressure and the water deposited at the poles. And it shows you that the thinner the atmosphere, the more water gets deposited at the poles, which is actually very interesting, because probably the atmosphere at the early moon was very, very thin. So that is a much more efficient carrier of water to the poles for the water to go, for humans to go there and actually find it and even use it. So I'm going to stop here, and I'm going to thank you for your attention, and I'm happy to take any questions.
Thank you, Kostas. That was a really great talk. Does anyone have any questions that they want to ask? I can't see any questions now in the chat. I guess I just have, without knowing a lot really of what you're doing in these last applications, I have one question in terms of, I mean, I guess with the Earth, the brood opposite circulation is important at transporting these aerosols around. What assumption is made about the circulation and these kind of other planetary applications in terms of how the aerosols are being transported, or are they just being kind of put in?
So the idea is that we trust what the model is giving, and of course it will probably not be the right thing, but there's no way for us to actually test stratospheric circulation or anything else like that. So given other constraints that we have about the planet's climate, we can gain confidence that the circulation is, if anything, at least a little bit realistic. So which means that the transport of aerosols is following along. If we go to exoplanets, then really we have no idea. We don't know what happens with transport there. We have way more uncertain things to worry about there from atmospheric circulation, but it is something that will be important here. And the only thing that we can actually do is sensitivity studies.
Yep. Great. Thank you, Kostas. So I can't see any more. Yeah, I can't see any more questions. So, I want to thank the speaker again and thank everyone for coming. This was being recorded, so we're going to post this within a few weeks on the GISS website, the YouTube website. So, okay, thanks everyone. Thanks, Kostas.
Thank you.
Bye.